Okay, everybody, and we're rolling. So right now I'm going to talk to you about the ice melting lab, okay? You should be watching the ice melting lab video after the solid liquid gas video, okay? Because these things are in order. All right. There we go. Yesterday, we had ice, and we put it on a hot plate, and we melted it, okay? We had a computer recording the temperature and we record the temperature every 30 seconds. Let me see if I can do this. Let's see if that gets that thing off film. It does. There we go. All right. So, this is what we use. And we put some ice in here. We flicked on the hot plate. And we had a computer readout of the temperature. And every 30 seconds, we took the temperature. Okay? Now, in the beginning we had ice and maybe just a touch of water in there. Well, this thing's not going to show us the temperature because it's saying the battery's dead. All right, I got it. Battery critically low. I get it. Get over it. All right. Anyway, so we had the temperature readout here. This is a little digital thermometer, and then we record the temperature until the ice melted all the way. Then we have water, and then it boiled. Okay. All right. So, we graphed all those dots, and after graphing all those dots, we ended up with a chart that looked like this, okay? And it's the chart you made last night in your homework, if you did your homework correctly, okay? We had temperature, and we had frozen water in the beginning, and it went all the way up to boiling. So you should divide this into 50, 75, 25, and then you can say, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90, 95, 100. All right? And then across the bottom, this took us about 20, that's not a straight line. It took us about 20 minutes to do it. 20, 10, 5, 15, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay. And then we even had 30 seconds in there, which would be those little dashes, right? So you can make a pretty accurate graph at home, and you did. So you should be looking at your homework graph that you made last night. Now here's the thing. I knew what your graph was going to look like because I know something about energy. Okay? Now, what was the ice when it was cold in the beginning? What was it? What form? Solid, liquid, or gas? Solid. So we started out as a solid right here. And guess what? Early on, you had a flat line like this. And then at some point in time, the graph started going up. Can you tell me when the line started to get steep?
Like just going straight up?
Well, yeah, when did it start to really turn and start going up? About how many minutes?
Like 7?
About 7 minutes. So about right here, we started going up, and then it went up. And when does this start up here? How many minutes? Or do we flatten out at the top?
10. Oh, flatten out. 17.
About 17? Okay. So there we go. So this is what your graph looks like. Okay? And maybe I can go over it with a darker pen. This is what your graph looks like, right? Maybe it's not exactly like this, but it's pretty darn close. You agree? Everybody with me? Okay. Now, Guess what? Looking at this graph, you can tell what substance it is and what's happening. I want to ask you a question. How could you look at this graph and these numbers and know that this was a graph about water? Come on. How could you look at this graph and know that this graph was about water? Okay. 100. So what is 100? Yeah. Well, you're like, oh, this flat point up here, it was remaining the same temperature. Guess what? It's probably boiling right there. And I can look right here and say that it's boiling at about 100. Water does that. And what about right here? What's this flat part down here? What's taking it so long to heat up right here? What's happening?
There's still ice.
Yeah, so what's happening? What process? Yeah, it's melting. So if we look right here, it's melting. So if I'm you right now on your graph, write melting and boiling at these two flat points. So you look at this, it's melting right at 0, and it's boiling right at 100. That's fresh water. That's what you would say. Mr. Perkins, I can tell that is a graph of fresh water. And I can tell because I see that it's melting and it's boiling. Okay? Now let me ask you a question. What is this steep line right here? Now, people that were in class, I said, look in your beaker, and when you see something happen, you're going to see the temperature start shooting up quickly. Do you remember what needs to happen right here for the temperature to start shooting up? The ice disappears. That's exactly right. So right here, you just have liquid. Does that make sense? So what is in, we're melting, for it to be melting, what two states of matter must be in the pot right here, where it's flat and melting? So, yeah, so you've got solids and liquids right here that are melting. Right here where the temperature is shooting up, you've only got a liquid in there. And for it to be boiling, what two states of matter need to be in the container right there? Liquid and gas, that's right. Liquid and gas. So look at all this stuff that you know just from doing this like very simple lab where we melted some ice until it boiled. You can make a chart. Someone else could look at your chart. Now they can see the melting point at the boiling point because that's where the areas are flat. Okay? Right? They can also know what you would see at the beaker at any point in time, and they know it's fresh water because they can read these numbers. Does that make sense? Now, you're like, Mr. Perkins, I thought you said there was a lot of chemistry to this. There is. And there's a lot of real math we could do with it. We're going to do that a little bit later in the semester. But the chemistry that I want you to understand is related to the last video on solid, liquid, and gas. Okay? And let's talk right now about why the lines are flat. Why are the lines flat right there? What's the real reason that this line is flat here, where it's melting, and flat here, where it's boiling? What's the real reason? Okay? Well, I'm going to sort of get you a little hint going here. I'm going to move over just a little bit. Here is our hot plate. I'm drawing a little picture of a hot plate right here, okay? Boop, and there's the button, okay? Right? And this hot plate was giving off heat. Do you agree with that? Now, another way to put that is to say that this hot plate was doing work or giving off energy. You can put it many different ways. So this hot plate's giving off heat. Evan, Did the hot plate give off more heat right here and heat it up? And less heat here and less heat here? Or did it give off the same amount of heat the whole time? The same. So this hot plate only has an on-off switch. So it's doing the same amount of work the whole time. But for some reason, the line is flat here and the temperature isn't changing. And the line is flat here and the temperature isn't changing. But the line is super steep here and the temperature is changing like crazy. Now, an elementary school kid would say, well, you turn the hot plate down here, and then you turn the hot plate up here and made it hotter. And then it started boiling, you turn the hot plate down again. But that's not the case. What is the case at these two flat lines? If this thing's giving off the same amount of energy, what does that tell you about melting and boiling? What does that tell you? It's changing phases, that's right. And what is required to change the phase of a substance? Energy. That's exactly right. So people, the melting and the boiling are processes that require energy. So the hot plate is doing work the whole time, the same amount of work. So right here, the work that the hot plate is doing is breaking these molecules apart and changing them from a solid to a liquid. Does that make sense? So right here, I've turned this on purpose. Now we can see superimposed over this. Now we can see superimposed over this the ice. And the heat here, the temperature is, the heat is being used to make these things break apart. Does that make sense? Right? Once we get them broken apart, once we get them into a liquid, then they actually get to start moving faster. That motion where they're moving faster, that's temperature. Temperature is really the kinetic energy or the moving energy of the molecules. So now we're seeing the molecules are moving faster. And then when we get to right here, it flattens off again because the energy from the hot plate is being used to do something else. What is the energy from the hot plate being used to do right now at the top? Boiling, you all said. That's right. They just couldn't hear you. People at home couldn't hear you say boiling very loudly. Yeah, so the energy right here is being used to boil. So even though this hot plate's giving off the same amount of energy the whole time, you do not see a steady increase in temperature. Work is being done here, and work is being done here that you do not see on the graph. Does that make sense? Does that make sense? Now, last thing I'm going to show you is sometimes you may say, I may give you a test question or something like this, and the graph look like this. Ready? Now, what's happening to this substance? It's being cooled off. This isn't boiling because now we're going this way, we're getting colder. So what's it doing right here? What's the opposite of boiling? Do you know the word for that? It's condensing. And then right here it's getting colder. I guess that's maybe too steep a line. All right. Right here it's getting colder. Right? So we still have liquid and gas here. We still just have a liquid here. And now we have solid and liquid here. Right? What's happening to it right here? No, because we're going the other way. Yeah. Now this point is freezing, right? And then down here you got solid ice. Solid, solid and liquid, liquid, liquid and gas. And we'll pretend that this one started up here. Now you just have a gas. Does that make sense to everybody? I'll make that straight. So you can go backwards too. Cassie, I want to ask you a question. Is this water that's being frozen on this graph?
Yes.
Does water condense at 75 degrees and freeze at 25 degrees? No. So this is some different substance. Does that make sense? Does everybody understand how you could infer that from the graph? So this isn't called a heating curve. This is called a cooling curve. So you can go up or down. But with about whatever substance you have, there's going to be a flat spot in two different places. Isn't that cool? Does that make sense? It doesn't look like this. It's not going to steady cool off. No matter what you're doing, there's going to be flat spots that represent, ready? Last thing going on. The flat spots represent what we call phase changes. Right? Phase changes. All right, cool.